This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is a supersonic nozzle. We're given that air flows through a converging, diverging nozzle, and the inlet conditions are a given pressure, 7 kPa, a given temperature, 420 centigrade, a given velocity, 400 meters per second, and the outlet velocity is 700 meters per second, which is supersonic, hence the name. The shape of this thing down here is the classic shape of a rocket nozzle. That's the converging, diverging shape. We're asked to find the exit temperature, and we're asked to find the mass flow. We're also given the inlet diameter. Okay, for a nozzle, the standard assumptions are steady flow, adiabatic, that is to say things happen too fast for heat transfer, and there's no shaft, so there's no shaft work. We're also using air, so we're going to include the ideal gas law. Now, to solve this problem, we're going to use an open system energy balance, and that says that the time rate of change of energy is equal to the heat rate minus the work rate plus the mass flow times several things: enthalpy change, kinetic energy change, and potential energy change. Let's use our assumptions and simplify this thing. If it's steady, then there's going to be no change in the energy in the system itself. If it's adiabatic, this term is 0. If there's no shaft, this term is missing. I'm going to cancel, now that those are gone, I can cancel the mass flow rate. And I have left enthalpy change, kinetic energy change, and potential energy. This is often neglected for gas flows. Neglect the potential energy change for gas flow. The gases don't weigh much. Potential energy has a small impact. What do we have left? We have left that 0 equals h1 minus h2 plus v1 squared minus v2 squared over 2. Now we're asked to find the exit temperature. We're going to look for the exit temperature T2 using the fact that enthalpy depends on temperature. So if I need to find H2, and then we can work on getting T2. All right, let's solve for H2. H2 is going to be H1 plus v1 squared minus v2 squared over 2. All right, we can find H2 if we can find H1 because we have the velocities. So we need H1 from a table. We're going to use the air table. At the temperature one. All right, let's go find an air table. Looks like this. This is the ideal gas properties of air, and it lists temperature in kelvins and enthalpy, what we're looking for, in kilojoules per kilogram. So here's temperature, and it goes down, and here's H, the next column over. We're looking for 420, we've given 420 C. We've got to convert that to kelvins here. So let's add 273. So we get 693, that's Kelvin. So that's the value we're going to look at. The table comes down and stops at 440. It picks up again over here and continues down. So I'm going to be looking for an enthalpy value between 690 and 700. So I need to interpolate between these two values here. So let me, I'll leave you to finish the interpolation. Let me just pull out the value that I got. So we're going back to the other document. I'm going to say that I have H1 at 693 Kelvin. I interpolated it to be 705.75 kilojoules per kilogram. And which table? This was table A22, and be sure to say which book so that somebody can exactly follow your work. All right, given that, now I can compute H2 to be H1, 705.75 kilojoules per kilogram, plus V1 was 400 squared minus 700 squared over 2, and this is going to be meters squared per second squared I need to do a units conversion there. I'm going to take meters squared per second squared. I'm going to multiply by newtons divided by newtons, and then I'm going to group this as meters times a newton meter divided by a newton second squared. Now, a newton meter is a joule, and a newton second squared per meter is a kilogram. So this guy becomes joules per kilogram. And I want to convert that to kilojoules by, well, let's do it down here. H2 is going to be 705.75 kilojoules per kilogram. If I take 400 squared minus 700 squared divided by 2, that's minus 165,000, and that would be in joules per kilogram. I'm going to divide by 1,000 joules per kilojoule, and now it works out. I can find that H2 is going to be 540.7 kilojoules per kilogram. Now I'm going to go back to the table. I'm going to say at H2 equals 540.7 kilojoules per kilogram. The air table gives T2 equals something. Let's go back to the air table. And again, which table? It's A22. Here's the table. Now we're at H is 540.7, so I'm looking in this column. 540 is going to fall between 533 and 544, so my temperature is going to fall between 530 and 540. I'll leave you to check my interpolation. Here's what I interpolated. I found that T2 is 536.5 kelvins, which is the same as 263.5 C. So that's the answer. I found T2. I had to use the table twice. And then I'll say note that the temperature goes down as the velocity goes up. That's the trade-off in a nozzle. All right, part B says, what's the mass flow? Mass flow is density times cross-section area times velocity, but we are using air. We're going to say that the density is the same as 1 over the specific volume, and the specific volume is, from the gas law, gas constant, temperature, molecular weight, and pressure. So let's find that. Specific volume for the gas at state 1 is the one we know. I'm going to use, why am I going to use state 1? Well, we know the area at the inlet. So V1, I'm going to use universal gas constant 8.314 kilojoules per kilogram mole per Kelvin. T1, I need to use Kelvin for the gas law, 693. Molecular weight for air is 28.97 kilograms per kilogram mole. And then we're told that the gas pressure at state 1 is 7 kilonewtons per meter squared, or 7 kPa. And kilonewtons and kilojoules go together to make what I need there. So when I crunch these numbers, I get 28.41 meters cubed per kilogram. And then my mass flow rate is going to be area, pi, entrance diameter 0.2 meters squared over 4, speed at entrance 400 meters per second, specific volume, which we just computed, 28.41 meters cubed per kilogram, and the mass flow turns out to be 0.442 kilograms per second. This is quite a large supersonic nozzle. That's a big mass flow. Let's recap. We're looking at a nozzle. We're given a lot of entrance information, and we're given the final velocity. To look at a nozzle, we need the standard assumptions for a nozzle: a steady flow, adiabatic, and no shaft work. We're using an open system energy balance, and when we apply those assumptions, the energy balance reduces to enthalpy and kinetic energy. That's the trade-off, enthalpy and kinetic energy. We used the air table to relate H and temperature in our solution, and we found that we're trading heat energy and enthalpy to gain a velocity rise. That's what a nozzle is for. It's for giving you kinetic energy. And if you remember that for a gas, you can pull in the gas law to do things like find the mass flow, then all will be well.